Hi, my name is Roger Espaza. I'm currently at Esperanto, as you can tell by the shirt. And I am here to present to you the work we've been doing in the Vector ISA extension in the working group, chaired by Christy. I'm the co-chair, and a lot of people have been contributing, so thanks a lot. And a lot has happened in the last few months. I think we've made a lot of progress. So let's go to it. First of all, just in case someone still doesn't know why vectors are good, which would be really surprising. But anyway, let me just go through it. Vectors, why are vectors good? Why should you have a vector extension in your next chip? Well, in case you don't know, by having a vector instruction that has one instruction works on a lot of data and does lots of things, you reduce your instruction bandwidth, you reduce your memory bandwidth, you, at the same time, you can do lots of things, so you can, at the same time, get a lot of data level parallelism exposed and then get low energy, and both things are actually possible together. And if the ISA is properly equipped, and it's not a crippled SIMD old-style boring thing, but if you have masks, if you have gather-scatter, and then you can pretty much compile any program that's really vectorizable into your ISA, and you'll get a lot of benefit from it. Now, that's in general any vector ISA. In particular, the RISC-V one, I really like it. Christy stole my thunder for the best ISA ever, but I'll repeat it. It's very small, and I'll try to convince you about that. It's got a very natural memory ordering feeling. A couple new things since last presentation for those of you that were here a year ago, or 2 years ago. The mask got folded into the regs. I'll talk about that. We got 3 types of data into the vector registers. And in general, you'll find all the things you need. And I'll talk more at the end about the best vector ISA ever. I have a few ISAs in my back, and I can say that with confidence. We do expect this to be fully usable, definitely in machine learning, which is the buzzword of the day, definitely in graphics, DSP, crypto. We've worked together with the crypto working group also, make sure that these things marry well together, and you can read the rest of the list. Okay, so let's get down to it. Well, for those of you that know nothing about the vector ISA, if you implement it, you decide to take it and do it, what do you have to add to your chip? Well, you have to add 32 registers, which we're going to call them vector registers, V0 through V31. Each one of those holds, obviously, a vector, right? But it can also hold a scalar value, and also we will make the extension such that they can hold a matrix. I will not talk about matrices today, but it's coming up in the spec. Now, a thing I really like about this new ISA, and credit here goes to Christy, is the fact that every register has an associated type, and we'll talk a lot about that and how that reduces the ISA quite a bit. Also, another thing is that you can have a variable number of registers. Maybe not everyone on their first VPU will do that, but that's something you can do, right? It is a vector ISA in the sense that there is a VL register, the vector length register, that controls every and all vector instructions. So that it is a classic vector. And as a good vector ISA, you can execute any instruction you want under mask. We'll talk about that. And pretty much you'll see that every instruction that you know in RISC-V has one in the vector ISA, counterpart in the vector ISA. So, okay, you decided you like the talk. You're going to build that vector unit. What do you put? As I said, 32 registers, and just for the sake of the explanation, let's think for a while that you decide that your vector is going to hold 8 things. Number one, the number 8 is not mandated by the ISA. You can choose any number you want, and you can do lots of cool things. But just for the examples, let's use the number 8. And maybe in this example, I chose that each element happens to be 32 bits. Next to each vector, we got a type, and you will implement 16 bits, maybe a few less if you're smart, next to each register that says this type contains a float 32, or sorry, this register contains a float 32, or this register contains an integer 8, or whatever, right? And then you also implement the VL register, which is XLAN, and a couple more bits for fixed point random mode and saturation. Okay, now that you have that new state, you've put that state in your CPU, what instructions should you implement? The base vector ISA is all completely here. So there are no, it's a bit cut? No, it's good. So on the far left in that kind of purple color, those are the 3 operand vector instructions, as you'd expect. We took out the F for FMAT. This is just multiply add because it's typeless. You got, I think you'll recognize every instruction there from the base instruction set. In green, there's a few instructions that take a single operand, a single vector operand. In, is that orange? Orange, a few instructions that take one vector operand and one scalar register as an operand, and then the memory operations. I'll talk about those, and obviously we have atomic memory ops also that are vector. And this is the full list. No, there's no other slide with 20 more instructions hiding there. And you'll see why this is so cute and so small. Okay, so let's start at the very basics. For those of you still lost that I don't know what he's talking about, what is this vector thing? I want to add two of these vector registers. Well, this would be the assembly for the instruction, vector add v1, v2, and produce a register in v0. On the left, you got the semantics in pseudo C. And if you don't like to read C, you can look at the picture. Basically, in the example, I'm saying, okay, we set, as an example, I insist the number 8 is not fixed in the ice. As an example, these vectors happen to have 8 elements. The current value in the vector length register for the example is 5. That has been set by the programmer. And so what is the instruction going to do? It's going to take the first 5 elements from V0, the first 5 elements from V1. It's going to add them pairwise, and it's going to produce 5 elements in the result V0. Now, also, a very important part of the definition is that what happens with the other 3 elements that are, I have physical flip-flops there, or SRAMs holding those values. What do I do with the other 3? And the answer for us, we want to enable out-of-order implementations of this, so you are mandated to put zeros in the result. That's not a choice. You cannot leave the old value. You will put zeros. Okay, that's the most basic one. Now, how is this executed? And 2017, and we still have this debate between SIMD and vector. Let's see if we put it to rest forever. How do you execute this? Any way you want. Let's say you've decided that you've built the register file I show you, and you've decided for your market you have 2 floating point adders in your chip. Fantastic. Then how would you consume the previous instruction we show? Well, it would take you 4 clocks, or we'll see. On the first clock, you take the first A and B, add them with their pairs. On the second clock, you take C and D, add them with their pairs. On the third clock, we had to do 5 things, not divisible by 2. Well, you'll do 1 division and put a 0. What will you do on the last clock? Up to you. Very smart implementations will skip the last clock. Not so smart implementation will just take it and put a 0. Now, you could also say, no, that's not my market. I need 4 floating point adders. No problem. We call that a 4-lane implementation. And in this case, you would just take 2 clocks, right? So in the first clock, you do the first 4 guys, and the second clock, you do 1 guy and 3 zeros. But okay, you're not happy. You want to do it SIMD. Please do. I mean, don't say that we don't support you. The ISA allows you to just put an 8-lane and just do all of them in one cycle, which is what SIMD is all about. Right? So you can do with this ISA any of these or all of them, or you can have different products in your product lineup with different lanes and whatnot. So I'm really hoping this slide puts the debate between SIMD and vector to rest, but I'm just an optimist guy. Okay, the next thing. The next simple thing. I want to add a vector with 1 number and a scalar. Very common math operation. Well, as I said before, we have 3 possible what we call shapes in a vector register. You've seen the vector register. You saw that it has multiple data. But you can, with that type info, you will be able to say, look, in V3, although it could hold 8 things, I'm only holding 1. And we call that a scalar shape. And that means that when you operate with that register, you don't get 8 different things out of it. You get always the same one, right? So let's see an example. Very simple. This could be a possible syntax. We have to talk to the assembly guys what they want. But v add v1, v2 is a scalar. And what happens? How did the picture change? Well, notice that in v2, instead of having 5 values in blue color, there's only 1 with the letter I. The other values in v2 have a question mark. Why do I have a question mark? Because the type of v2 is a scalar. So there's only 1 value. You, as the implementer, can do whatever you want with those question mark boxes. You, for example, a very clever thing to do would be to take I and just replicate it across. Why? Because then you don't have to be broadcasting wires from strange places to other places. But you can do whatever you want. So what does the operation do? It takes the 5 elements of V1, adds all of them with I, which is the one and only element of V2, and you produce 5 results. And as before, you are mandated to write zeros for the rest of the result. Okay. The other thing you need for a good vector implementation, you need masks. What are masks used for? To compile loops that contain if statements, right? So for mask execution, a decision we made recently that we're very happy with is that we're not going to have, as many vector ICs have had in the past, separate mask registers, right? When you compute a mask, it's just a normal operation. You compare 2 registers, and what do you get out of it? A Boolean. And we'll represent that Boolean as an integer. And that integer just matches the C semantics. And that integer goes into another register. Now, some of you will complain like, oh my God, you're wasting 32 bits to remember 1 bit. That's unacceptable. We think it's actually a very good thing. It simplifies a lot the ISA. It's going to make you happy when you're building the vector unit. Trust me. So basically, what do? You do vector equal V6, V7, and you put the result in V1. And you get a vector of zeros or ones. That's all you do. Now, how do you use V1? Well, every instruction has 2 bits in the encoding. So every single instruction can say, I want to execute normally, which is what I've been talking about. You set those 2 bits to 0. Or you say, well, I actually want to execute under mask only under control of the V1 register, right? So let me show you that in a picture. It's going to be a little better. So you would say something like this. I want to add V3, V4, but I only want to do it for those values of V1 that are true. That's the v1.t notation there. We'll see what the assembly guys decide in the end, but that's what we're going to do. And you see in the picture, you would do the additions. Actually, if you were smarter, you wouldn't do all of them. But the results you're going to write, look at V1. V1 has a bunch of ones and zeros. The positions in the vector that have a 0 actually don't get the result of the addition. They get what? A 0. Again, another decision to help out-of-order machines, right? So if it's masked out, it didn't happen, you write a 0, right? Okay, enough arithmetic. Let's go to vector loads. So the most fundamental thing you want to do, load. I should have started there, but I think it's easier to go first through arithmetic. So you want to load some data into your vector register. Vector load, the basic one. How does that look like? Well, it looks like a load. It has a base register, x3, that has a full address. It has an immediate. And you go off to memory at that base address, and you load a bunch of numbers. How many do you load? You load as many things as the VL register tells you. In my examples, VL is always 5. So we're going to load 5 things from memory. Where do you load them from? Well, the first address is 100. Why? Because x3 is 20. The immediate is 80. That's 100. And then, so you load 4 bytes from 100. How do I know I load 4 bytes from 100? Well, I know from the type, which I didn't really explain yet. I look at V5 and say, oh, look, this is an F32 data, so I need to load 4 bytes. Where do I get the next thing? This is called unit stride. The next thing, you increase the address by, if you follow the code, by size. And size is the size of V5. So you'll load from 100, 104, 108, blah, blah, blah. That's how you load the vector. What do you with the rest of the vector? Again, use 0. Whatever's past VL, you get a 0. That's the easy case. Now, the more interesting case, or very useful case, or very needed case, is a strided vector load where you can actually provide a second scalar register, x9, which contains the stride. And that tells you how far apart is your data in memory. And for the example, and due to the PowerPoint limitations, I made a small stride. X9 is 8. Is the stride in bytes. So you take the first address, x320 plus 80, that's 100. And to compute the next address you want to go get to memory, you add the stride, right? So 100, 108, 116, and so on and so forth. So you load the elements and you 0 the rest, right? Okay, those of you that know vectors are like, wow, this is boring. So yes, it's boring and it's nice. Okay, the next one, the next thing you need. A gather, and to not call it a gather, but that's what we call it. It's an index vector load. In this case, it looks very much like the strided vector load, but it's a lot more interesting. Now you have a base address, x3 plus 80, and you use v2 as an offset from that base address. That allows you to load arbitrary data, as long depending on the size of V2, at the locations indicated by V2. And V2 could contain offsets that are actually repeated. That's legal. Or there are, that are in any order you want, right? Your machine is going to go and take, is going to take the base address. It's going to add the first offset, 8. It's going to take them together and get you that piece of data and load it, right? So that's a gather. And I should have said in the previous slides, I'm sure you read it, unaligned addresses are legal, as in the base RISC-V address. Do not expect a vector machine to go fast if you feed it unaligned address, but that's an implementation choice. You can obviously, burn more hardware and make them go fast. For every one of these 3 that I explained, we got vector stores, the corresponding stores. So you can take a vector, obviously, and send it to memory. Now, an important difference here, if VL is 5, you write 5 things into memory. You don't put more zeros at the end. That is a huge difference between the load and the store. I know you knew that, but it's worth repeating. We got, obviously, the strided vector store, so you can put 5 things in memory separated by a constant stride. Or you can do a scatter, which is an index vector store, which is, again, you give it a bunch of offsets, you give it data, and it will write. Now, the scatter is more interesting because in the load case, if you got multiple addresses, multiple offsets pointing to the same position, you could ask, well, OK, I get the same data twice. What happens if you store 2 things with a scatter that point to the same thing but have different values? Well, that's a bit more interesting. And we will probably, this is not fully closed, but we will probably have 2 versions of scatter. The unordered scatter, where you're not guaranteed which one will end up in memory, and the ordered scatter, which will tell you, yeah, it's in program order, no surprises. And it's likely that this latter one is going to be a little bit slower. OK, so we covered all our memory operations. I don't have slides for the atomics, but I'm sure you can guess. And now, at the risk of offending the ordering guys, we just put 4 bullets not to get in trouble. But what's the memory ordering that we want for this? I think the summary is, think of a vector load and a vector store as a loop doing memory references. So if you are a memory ordering expert and you have a loop of stores followed by a loop of loads, what do you expect? In RISC-V, we expect that the later loop full of loads will see all the values of the previous loop full of stores. And that's what we're asking you to build, right? You can reverse it. If you got a loop of load followed by a loop of stores, the same thing you'd expect from the base ISA, this is what you get. It's not the ultimate fastest option, but it's very clear and it follows the baseline, right? So we could have done it a little bit faster, but I think that's good. And from the point of view of other hearts, same thing. Think about those 2 loops. So what would you think from a remote processor? Well, whatever you think you would see, that's how your vector unit should behave. That's nowhere near making any justice to memory ordering, but I didn't want to get into trouble. OK, the types. I really like this feature of this new ISA. What does it mean to have a type vector register? Well, we've said each vector register has a type, right? And you can have V0 be a floating 32 and V5 be an integer 8. That's legal, and you can manage that. The types you are required to implement are in the table below. So based on your scalar processor, and if you have a scalar processor that's RV32i, these are the types that you should build in your vector unit next to it. So it makes sense based on the vector ISA what you should build. And now, wow, if we have different types in the vector register, what happens with an instruction where you give it V0 and V3, and those things have different types? We'll get to it in a second, but some combinations are legal, some combinations need to convert. So let's do first the easy one. Let's start with convert. We've got rid of a lot of opcodes that you can see in the baseline ISA by saying we're going to have a single convert instruction that takes one vector register, looks at its source type, and I'm using these sub-indices to say, imagine V1 was an F32. If you convert V1 from an F32 type register to V0, which happens to have type F16, what's going to happen? Well, what you guys expect. We're going to take the F32 values, we're going to down convert them to an F16, and we're going to stick them into V0. That's the point of the instruction, right? So the expected converts just work. There's an additional feature where you can sort of change on the fly the destination register type. That's sort of a little bit secondary thing. Now, that's the obvious thing. We could just say that's all we give you, but we added a little bit more and said some easy combinations of types will allow you to just mix in an instruction. So for example, you will be able to say, I want to add V1 and V2, which are both integer 8s, right? And I will put the result in an integer 16. And in this case, the way to think about it is the integer 8s being integer, signed, gets sign extended to 16 bits. The values from V2 get sign extended to 16 bits. You add them in 16 bits, and you create a 16-bit result. And you have a matrix that probably you cannot read, but trust me, it says the T's mean trap, so that's not a legal combination. The P's means pass through, which means it's accepted. And then SE is sign extend, and Z, zero extend. And we actually also allow adding an F16 with an F32 into an F32, or probably the machine learning guys will quickly recognize multiply add 16, 16, and adding into 32, accumulating into 32 and leaving the result in a 32. And for those where you just have to rebias the exponent, that's going to, and obviously put zeros at the bottom of the mantis. That's also going to be legal. OK, more interesting stuff. The other thing you can do is that the vector register file is not set, the size of the thing is not set by the ISA. So the ISA is not telling you how big the vector register file has to be. And that's very nice because basically what you do is you, as the implementer, say, well, this is my maximum size. And the programmer says, well, this is what I want. I want 4 registers of type F32, or I want 32 registers of type F32, right? So we'll probably be making a few changes on that config register, so that's probably going to be a little bit change in the final spec. But fundamentally, the programmer will tell you what it needs, and you, the implementation, will respond to that CSR instruction by saying, OK, so this is the maximum vector length you're going to be using, right? And that, I'll walk you through the examples, but the way to think about it is that you can make a very simple implementation where you always do the same, or you can make a very complex implementation like Berkeley's Hwacha, that you pack the registers super well based on the size of the data, and then you maximize the usage of your vector register file. Right? So let's go through examples. It's going to be easier than just listen to me. So let's say the easy case. You've built 32 registers. You've decided that all the money you had allowed you to have 4 elements per vector and 4 bytes. So you've built this structure in Harvest that has 512 bytes of storage. This is the real thing, right? Now the software goes and says, well, I want to run a loop with 32 F32 registers. Well, this is what your hardware will calculate. OK, I need 4 bytes for the V0. I need 4 bytes for V1, 4 bytes for each element of each register. You do the math, which you've done while I was talking, and you'll see, oh, if he wants 32 registers and I have 4 elements, the MVL, the maximum vector length, is going to be 4. Now, how is that organized in a vector register? Here's a possible picture. That's an implementation. You are not constrained by my picture in any way. You could have 4 SRAMs, 1 per lane, and you just put 1 element of each vector in each SRAM. So this works really well. That's what you'd naturally do. Now, what if the user, a little bit more interesting loop, the user doesn't need 32 registers? The loop, you look at the loop, and the compiler says, wow, I can do this loop with just 2 floating point 2 registers. Well, let's do the math again. Now, you need 4 bytes per V0 element and 4 bytes per V1 element. So how long could you make each vector? In theory, not in theory, you can make each vector 64 elements. So advanced vector implementations will actually go ahead and say, oh, software, you can process this loop 64 things at a time. Now, how is this organized? Well, many possible ways. For PowerPoint reasons, I chose to color them inner leaf, right? But you can put them together or any way you want, right? So I've decided that a possible implementation is to put 4 of V0, 4 of V1, 4 of V0, 4 of V1, right? Now, don't be scared. The last thing I want from this talk is to be like, oh my God, when he started doing colors, I'm not doing a vector unit. It's legal. It's legal for you to say, I don't care. You just want 2 registers. You get 2 registers, and we're going to waste the rest of the space. Too bad. I mean, that's probably what you'll do in your first implementation. Maybe the second one will say, wow, let me go read those slides with colors again from 2017. I think there was something there. So that's legal. It's up to you. You, the hardware, respond to a configuration request for the vector unit by giving back the maximum vector length, and software just uses that. Last one. I promise to finish with this one. More complicated, 2 F16 registers and 2 F32 registers. Well, you'll do some math. You'll see, oh, I need 2 bytes for the F16s, 4 bytes for the other ones. That's not a power of 2. Let me round up to a power of 2. And what you'll say is like, look, I can give you a maximum vector length of 32. How you organize it, I changed colors one more time. In this case, I put the registers, all V0s together, all V1s, then the V2s, then the V3, and there's a little bit of empty space in your register file. Again, completely up to the implementation. This is your problem to solve. The ISO won't tell you how to do it. What you should get from this long series of examples is that all vector registers, regardless of their type, so don't be confused by all SIMD, have the same length, right? So once you've set this up, you got 32 elements for the F16 guys and 32 elements for the F32 guys. So you can operate with them, and it makes sense. The semantics just make sense, right? Okay, moving on. Now, how does software use that? Okay, they said they wanted 2 registers, and they've configured the vector unit. What do they do next? Well, they use the setVL instruction. The setVL instruction, once you've configured the vector unit, the setVL instruction sets the VL value and takes into account the MVL that the hardware has computed. So that happens all in the microarchitecture. So when you say, hey, I want to work on 1 million elements, I want to add 1 million vectors in memory, and you stream-mine the loop correctly, when you set VL, and this is the example we have in the spec, the first thing you do in the loop is you set VL, and that value A0 could start at 1 million. So you say, hey, I want to do 1 million things. And Harvard says, yeah, I'm sorry, I know you want to do 1 million things, but we'll do them 32 at a time. So the real set VL, the VL that gets set is 32. You loop around, you subtract 32 from the total count. You loop again and say, oh, now I have 1 million minus 32. Can we do it? And the Harvard says, no, we'll do another chunk of 32. And you keep looping and looping until at the end you got, I don't know, 7 elements left. Okay. Wow, the colors are really horrible. Let's see. Encoding. We've closed on an encoding. We're going to take 2 major opcodes only, one for VOP and one for VMEP. Thanks to these types, the encoding really shrinks. I really like it. And don't want to bore you with it, but it's fairly standard. Maybe we'll move the immediates a little bit. The encoding for the atomics follows the baseline encoding. So it's all, I'd claim it's very standard, and you'll see no surprises here. What else? Not covered today, exceptions. I got a couple good questions in the breaks even before the talk. We haven't covered exceptions. We haven't talked about kernel save and restore. Custom types. The reason for having such a large 16-bit type field, or someone might ask, come on, 16-bit, that's a lot. Remember what we have in there. We have the type, we have the shape. We need some bits to say whether it's a scalar, a vector, or a matrix, which I'm not discussing today. We might need to store there also the maximum element size to allow easy and fast converts. Now, the types, we will allocate enough bits, and I'm hoping the foundation will choose encodings for lots of types. So in particular, now that Dave announced what Esperanto is doing, we will have types, or we're going to allocate types for strange types like unorm24. If you don't come from the graphics world, you don't know what unorm24 is, but it's a very needed and useful type. And other people will create other types, and hopefully the foundation will just keep the type encoding. It's not going to tell you, you must implement this. This is your choice for your market, for your segment. That's what we're going to do. OK, what else? Status and plans. I'm lucky. So I will defend it's the best vector ISA ever. A little bit of boring personal history. My first vector ISA was for the alpha guys, showing my age here. That was a very nice one, very clean, similar to this one in some aspects. Then that ISA ended up at Intel when Alpha was acquired by Intel. We did another vector ISA that never made it into Nihilum. Then that one, we did another one for Larrabee, or I did another one for Larrabee with other folks. Then that became AVX 512. I've got a number of vector ISAs and scars in my body from corporate fights, and I can tell you this is, I claim this is by far the cleanest one we've done so far. So, or at least I've been involved. So really, really good ISA, I think. We promise to have a spec ready for you by next workshop. And if you go to the GitHub right now, it's way out of date with respect to the slides. We promise to fix that very, very soon. And a few things about software. Hopefully, we fully expect LLVM to support this, and I would love GCC Auto Vectorizer to target this. And as soon as possible, we'll get the spec, the encodings out, start getting the basic tools out so some people can do some testing. I can say a little bit for Esperanto that we're definitely coding this in RTL. We have an early version of these, and we're trying and we're feeding back everything we can to the working group to make sure that it's useful. So, if you didn't like it, which shame on you, please join the working group and complain. Come to us and say, this is wrong. We should do it differently. I need this for my market. Please come join the working group. There's a mailing list. You can just join and come talk to us. And I got 1 minute, 30 seconds for questions. No questions, Rick? One question. Come on. Go. The intention, what happens with page faults and exceptions in general. If you're doing a vector load, the intention is, the easy answer is to tell you it's precise. Now, exactly how do we make it precise? If your hardware page walker, the TLB page walker, can solve it by itself, fantastic. Nobody will ever know you had a TLB miss in the middle. Now, if the TLB miss resulted in a real page fault, what we probably will write in the spec, it's not closed, is that we will tell you where that fault happened, and you should be able to restart from that position when you come back from supervisor mode back into user mode. You should be able to restart from that position. So you'll have to have a new state in supervisor to say, look, of these 8 elements or 32, we did the first 17, and the 18th had a problem. So when you restart from the 18th. There are other alternatives. What we did, for example, in Larrabee, which is keep a mask of which elements we've done. But maybe this one's more nicer. But not fully closed. But our intention is to be precise. That should be clear. OK, thank you very much.